The tool is using digital maps as a baseline input. So you're looking now at a digital terrain model, 2-meter resolution. So you can have a clutter layer on the top. So now you're looking at the terrain and the clutter. So clutter is just a classification of the environment. So now I'm looking at the clutter settings. Can define different attributes or different characteristics, different RF characteristics, such as reflection coefficients or clutter height. Clutter height is allowing you to add a diffraction component to your predictions. So reflection is very useful when you do 3D ray tracing or reflections multipath. So it allows us to establish what is the strength of the echo bounced on the surface of a building, for example, or surface of the water. So we can have different attributes here to model this. Now, regarding the Z dimension or the height dimension, we have a separate layer. So I'm going to talk about all the layers. This is what we call the building layer. So this is capturing only the buildings, and also we capture the vegetation as well as a individual elevation information per pixel. If I zoom in to show you, so now you're looking at the pixel. 2 by 2 meters in the reality is equivalent to 1 pixel. 1 pixel can carry only a single elevation. So everything is based on a grid, a raster. Now let's talk about the building. So this is the building, and the building is helping to add obstacle to your model. I'm going to run a dummy virtual profile. Okay, I'll put 2.4 gigahertz, 1 watt transmitter, transmission height say 100 meter, and receiver is 100 meter. I'm just going to show you what's going to happen when I run profile from one point to another. So put the receiver height to 100, and then you can see what's going on. So if the buildings are there, then it will calculate. See here the diffraction. It's no more free space conditions. The red is free space model, and then here is the model we have. On the left-hand side, you've got the transmitter. On the right-hand side, you've got the receiver. The green is the vegetation, and the gray at the bottom is the digital terrain model. Now, on the top of this, we also have the image. We've got here a Bing hybrid, Bing aerial. We've got Google hybrid. Okay, this allows you to check if the building is the latest one. Or now, also I wanted to talk about another layer. We call it the vector layer. Allow you to define a boundary, a polygon, points of interest, and this can be very handy. For example, if you want to do analysis and you want to restrict the analysis to that area, percentage of coverage inside that polygon, it will become very, very handy for that purpose. You can batch report the numbers and stats inside these areas. Now, on the top of this, we have the propagation model engine. You see here we have massive library of propagation theories. So all of this you're looking at is out of the box. So HF, for example, we have skywave model, we have ground wave models such as ITU 368, which is dedicated for ground wave. We can import the conductivity, the permittivity of the land, of the area. So you can see here we have some propagation models like ITM, NTIA. This is commonly used in the US by FCC and NTIA for coordination and for prediction of coverage for mission critical networks, public safety networks, and also for broadcasting. We have this guy here, 1812, also European model used for terrestrial system. We have 452, commonly used for interference analysis between terrestrial systems. We have ITU 5 to 5, 5 to 6, which is a geometrical models. Statistical models are based on statistics and usually do not follow the terrain, do not follow the buildings. Whereas if we're talking about ITU, for example, 5 to 6, 5 to 6 is a recommendation from ITU, which is dedicated for diffraction. So this is the kind of propagation models, such as Dago 94 method. So Dago 94 is an excellent diffraction model, which can calculate diffraction on multiple buildings. Lateral diffraction is on the side of buildings. So I will show you how this is all working together. This is the propagation model. Also, you can do ducting. For example, if you're going to talk about jammer, for example, and you are worried that your jammer might overjam or might propagate beyond the designed area across the water, yeah. So you can also do ducting analysis. So your system might be a combination of, say, jammer, DF, radar, or maybe just a Wi-Fi communication. We have the delta N model for the first 1 kilometer of the atmosphere. So this is a propagation model I'm going to use, okay? So let's have a look at the stadium. So I'm going to overlay my building layer, right-click, add the XRX. I'm going to add a device. I say it's a Wi-Fi, okay? Now I've got here my sensor, or let's call it here my UAS. Maybe we have more, so we can add more. Downlink coverage down to the controller. Let's go get the coverage, and let's define the height of the controller from the ground. And let's go up to say 5 kilometers. And after that, I'm going to here. I'm going to define your antenna gain at the controller. It's all done here, and bingo. So now I send that controller to every pixel within 5 kilometers. And I ask him to predict for me the signal in the downlink from the UAS down to the controller. Here we go. So this is your coverage. You may need to change the sensitivity. So this is where you do it. Neg 98, then say it's neg 88, and say neg 78. So I'm going to make a copy of it. Here you go, stations. Okay, so we can probably change the height if you want here. If you intercepted the height here at say 50 meters, okay, at this position, using camera or direction finding or whatever, and now let's go perform the coverage based on the 1.5 meter height, 5 kilometers as well. So when they finish, I will ask for the overlap analysis. So overlap means it will count how many signals exceeding the threshold. You see here we have something called simultaneous server. Counting, you can only communicate with one position only. How many stations same? How many UAVs positions you can talk to simultaneously. So let's look at the outcome. So red means 1. If you are a controller and you are in the red zone, so this is 1, and say this is one we call it 2. Okay, this one we call it 2, and then this is number 3. Let me just name them. All right. So red is that means the controller sitting in the red area can only talk to one UAV. The blue area are areas where you can talk to 2 UAVs. If I run for you something called connection, real-time connection, allow me to analyze. You see, I can study the area. This is a real-time function, a location for the controller. If the controller is here, hard luck, no one, you can talk to no one. So viable target or viable location. The red area, you see, you can only talk to one UAV. The green color, I'm going to change it to maybe yellow. This park is such a nice area to talk to all 3 locations. And these are the different spots. So look, even if you want to import these locations from CSV, it's easy. You go import stations from CSV, from generic file. So you can easily just point to software, and then you match it. So it allows you to overlay this or to import these positions of the UAS on the map directly. If you have the journey, if you have the path, the flight path, for example, it's also possible to do things in that mode. So it's possible to draw something like this. So you can do something like this. Go back to the path. You can set up different. This is waypoints, and then you can put different altitude: 100, 120, 160, 160. Okay, above ground level. So you can do this, and then you can analyze the communication in that mode. So this is called path coverage calculation, waypoints, based on 5 kilometers. Maybe let's make it 3 kilometers only for now. And let's do it based on neg 90, we said neg 98, which is 45, okay. So here we go, let's go back there. Path, and then path coverage calculation and simultaneous coverage. 1.5 is the remote controller we're looking for, and let's go. So obviously the first point was not flying too high. You see, the lower the height, the more time it takes, because the software has to compute more diffraction. So this is exactly what I showed you before, but it's more automated. You draw a flight path, and then you can reverse compute the signal, and then look for the simultaneous coverage. Here we go. This heat map is based on percentage. So here 100% means six points. So obviously you can do 100 points, you can do 50 points. This particular location example is covering all 6 points. So that means it has maximum chance to locate the controller in their area. And when we say 50%, that means half of the waypoints, which means 3. Okay. The heat map is actually the percentage. You see on the street you got better coverage. So we have a 3D view, and you can actually, you can put your head, literally put your head in the camera, and then see the world from the same lens. You know, you can see what is your visibility like. Yeah, I'm running now the rendering. This is a 3D coverage. I mean 3D map constructed from the setup. You can see your. You see here we've got. You see this. I think these are DFs installed on the rooftop of the buildings. And yeah, let's see. In the view here, we've got the path perspective, but you can see you can roll, you can turn around, you can adjust the tilt. There is a function to allow you to see what the antenna is seeing, or what the camera is seeing. Station site search, intervisibility. So intervisibility is site coverage kind of. We also can do it from here. You can click on the station, and then you go to coverage, or here site coverage. The site coverage has become like optical. You can put a target, say target is 100 meter. So this is now just optical coverage. So you can see, for example, here there's no path. Here there's path fly 100 meter. You see how it's nicely clear.